Hello everyone, we will continue with our lecture series in this optimal control guidance and estimation course. So far you have seen many concepts including linear quadratic regulator for about 2 lectures, and we will continue the discussion on LQR in this lecture as well actually. So, this is what is coming up today, I mean this lecture. This is outline of the lecture. First is the review of LQR using state transition matrix approach. That means, whatever we discussed last lecture, we will have a quick review of that, because we need to use that next for tactical missile guidance application as well. This is just an example of how optimal control gives us a platform to design advanced guidance laws and all that. More on that we will see little later, but one approach using state transition matrix we will discuss in this lecture actually. Then towards the end of this lecture, we will also talk about frequency domain interpretation of LQR as well as some robustness property results actually. Okay. So, how frequency domain interpretation people do that, because typically when you talk about linear systems, then this Laplace transform and other things will come into picture there. So, we will have some idea about what people talk about a frequency domain representation and how it leads to some sort of a equation using which you can also design the gain matrix actually. We will also give an example on that. Alright, so first is the summary of what we discussed last time. This is what we discussed. The standard LQR problem. We have a quadratic cost function, penalty function at the end, and cost function for the path actually. And the path constraint happens to be state equation. Boundary conditions are given like this. This is the standard form, standard equation that we have been discussing under the framework of LQR. And here we will talk about soft constraint problem. That means x of Tf is actually free, it is close to 0 by this minimization, this term minimization actually. Okay. So, this is the problem that we are talking under the framework of soft constraint. So, we went ahead and derived all these things. First of all, we noticed that this is phi of x f, this is L of x u and all that, and using which Hamiltonian was like that, and then these necessary conditions state, co-state, turn optimal, that turn out to be like this, and then the boundary conditions happens to be lambda f equal to S f x f. After that, we went ahead and substituted this control expression in this state equation, and then we could notice that this can be written as something like x dot lambda dot as a coupled set of equations like this, where this is the AA is nothing but an augmented system dynamics sort of thing. And because it is a homogeneous linear system, we can also write the solution in the form of a state transition matrix, and hence we can write lambda x and lambda at time t is nothing but phi of t Tf and x and lambda at time Tf actually. By the way, just a comment, some people intend to write it as something like a initial condition also. In other words, it will be phi of t t0 and then x lambda of t0. Okay. Again, it depends on your situation and then which is advantage to us and things like that. Sometimes in the literature you may see something like that. Both are correct actually. Anyway, so writing this way, then we could partition this matrix as some phi 1 1, phi 1 2, phi 2 1, phi 2 2 sort of thing. And then we could notice that using this boundary condition lambda f equal to S f x f, we can also write this kind of equation where x of t is dictated by x of f through the state transition matrix x of t Tf actually. Now, this algebra we discussed last time already. And then similarly, we can also write lambda of t, the second half of the equation, and through a fairly similar algebra, okay, leading towards that actually. Okay. So, when we do that, when we write it something like this, then x of t happens to be a state transition matrix times x f, and lambda of t happens to be another state transition matrix times x f again. Remember, this is not lambda f, this is x f again. So, at t equal to T f, it must satisfy the boundary condition x equal to x f and lambda f equal to S f x f. So, we can get this final boundary condition as well actually. Using this boundary condition, this turns out to be the boundary condition for this. And also we note that the state transition matrix will satisfy the same differential equation basically. So, we have a differential equation and we have a boundary condition. So, essentially you can integrate it backwards and then store the solution and things like that actually. The problem however is xf is not known basically, okay, because ultimately after getting the solution for the state transition matrix, still the solution for x of t and lambda of t requires the information about x of f. X of f is not known. So, how do you handle that? Because now it is easy for, because the state transition matrix representation allows us to write it this way as well. X of t 0 equal to x of t 0 t f into x f. Now, that is valid because this expression is valid for any time, including initial time. So, we put initial time condition here, then you will get x of t 0 equal to x of t 0 t f times x f. So, that is what we write it here, and typically state transition matrices are never singular. So, we can always invert it and then get it this way. Okay. So, x of f is x of f information is available now. So, we can go back to that and then write x of t and lambda of t as something like this, okay, because x of t and lambda of t is already there as an expression. Now, we got x f. So, using that expression, if you substitute here, you get the expression for x of t and lambda of t like this actually. So, finally, we have the control expression u equal to minus r inverse b transpose lambda. So, you can substitute this lambda of t, because you got lambda of t here like that, okay. And then you can always define this matrix what you see here as some sort of a gain matrix k of t, and hence you can write minus k t times x 0. And again it gives some sort of a sample data feedback law, and if you consider wherever you are I mean wherever the condition is, that being the initial condition, then you can represent this this control law as something like u of t equal to minus k t into x t. That is how we get the gain matrix for this actually. Now, this is all about soft constraint problem. How about hard constraint problem? We also discuss about that, and it turns out that this class of problem demands that there are part of the state vectors is equal to 0 at t equal to t f, and hence we have this sort of a formulation, okay, which talks about I mean the regular standard LQR problem. However, the boundary conditions demands that part of the states is equal to 0, and that dimension of that subset can be as high as n actually, and in other words the entire state vector can be constrained if it is necessary to do that. Then the regular I mean the analysis we discussed about that in last class. Turns out that because of this hard constraint, we have to augmented I mean the cost function turns out to be something like this, where nu I happens to be additional Lagrange multiplier sort of constraints actually. Okay. Then we carried out the similar algebra, but the boundary conditions turn out to be different. In other words, we have this first 1 to q x of t f equal to 0, but after that q plus 1 to n x of t f equal to 0, I mean lambda of t f equal to 0. Okay. So, it account for all that in the solution procedure. Then you now what we did is we collected the terms of these quantities which are non-zero, and then defined this mu vector as something like this actually. Okay. Then using this mu vector, we could write this x of t and lambda of t as something like this, and then the analysis were fairly similar to what we had before. In other words, the state transition matrices will satisfy the same differential equations. However, the boundary conditions turn out to be something like this actually. Okay. The detailed analysis and derivation and all we have already done in the last class actually. So, because of the boundary condition difference, okay, it leads to a very different solution actually. Okay. So, now it turns out that we cannot always claim that this x of t 0 t f remains singular, I mean non-singular, but if it remains non-singular, then this expression is valid, and in that case we can always write this actually. Okay. That means the form of the solution is fairly similar to what we had before, but the real actual values numbers will be different because the boundary conditions are different actually. Again similar to previous analysis, the continuous in case of a continuous data, that means we have this t 0 goes to t and all that. Okay. There is a small typo error probably. This is to be u. Okay. All right. So, that's a small one. Okay. So, this again if you take wherever the state is, that being the initial condition, then you can write the control as something like this. Now, here the problem happens that as t goes to t f, then this approaches that, okay, but x of t f if you see the boundary condition, it has a bunch of rows actually, with bunch of rows which are zeros. So, essentially x of TF is nothing but a singular matrix, okay, and hence there is a problem at the end actually, but that is expected because the ambition was little very high. In other words, we insisted on 0 terminal error actually. So, I mean, if you have a soft constraint, this problem typically does not arise, but if you have a hard constraint, this problem does arise actually. Then the usual approach is after some towards the very end, when T approaches very close to TF, then you do not update your gain matrix, you just use the previous gain matrix and all that actually. Okay, so that can be some sort of a what I call as engineering fix actually. So, in practical problems, typically you can do it and mechanize it that way. Okay. But anyway, so this was the summary of discussion last time, and this class I would like to use this concept and then apply this through an example, a good example which talks about optimal missile guidance through state transition matrix solution of LQR. So, let us see how the formulation is and where it leads to and things like that. Now, what is the fundamental of tactical missile guidance? The situation in a 2D plane, in the plane of engagement, assuming that it is some sort of a 2D engagement towards the end, we can write it this way. So, there is a reference line typically parallel to this horizon sort of thing, horizontal line, and then there is a missile, okay, which is chasing a target. Okay, it is a there is a missile and there is a target. Okay. So, it is chasing a target. The target is running away with velocity Vt with an angle theta t with respect to what is called as line of sight. This LOS stands for line of sight actually. And similarly, the velocity of the missile is something like Vm, which is a different angle theta m, and the way it corrects the direction of Vm is through applying this lateral acceleration Am. You can think of something like a centrifugal force and things like that way. So, with the moment you have some sort of a acceleration that is perpendicular to Vm, then it will try to rotate the Vm vector. So, remember we do not have a thrust vector control and things like that. We do not have a thrust manipulation control, means Vm typically is not controlled, because there are several reasons for that. The thing is, it is not a very good control manipulation thing, and you cannot manipulate it as you wish in a fast dynamic sense. So, the Vm is typically left it as it is sort of thing. But assuming that Vm is larger than Vt, that means Vm is moving fast compared to Vt, then there is only the direction correction of Vm will typically lead to engagement. And this concept relies on something like rotation of line of sight vector. This line of sight vector that you see, rotation of line of sight vector actually. That means, if the line of sight vector does not rotate, okay, then ultimately it leads to something called a collision case, and it leads to a collision triangle sort of thing. This is what happens actually. If it does not, if you start rotating the Vm vector properly, okay, manipulate properly, then this is what will happen. In other words, if this is your initial LOS, after some time this is your LOS, that is your LOS, that is your LOS, like that. All these after some time they remain parallel, and your target appears larger and larger. That means, you are approaching the target anyway. Okay. So, ultimately it leads to collision at some point of time actually. Okay. So, that is the whole idea. The whole idea tells us that somehow I have to apply some sort of a lateral acceleration. This Am is called lateral acceleration to Vm. Okay. And so that the turning will take place, Vm turning will take place, and ultimately it leads to a collision actually. That is the whole idea of tactical missile guidance. There are several variants of that, of course, and then one of the variants will talk that Am should be applied perpendicular to LOS instead of perpendicular to Vm. That is geometrically more correct and then more precise also. But applying a perpendicular vector to Vm is practically easier than as compared to applying something which is perpendicular to LOS actually. So, there are again mechanization issues and all that, and there are also results which shows that it does not really matter. What will matter is the magnitude of Am will vary in such a way that ultimately both will lead to the similar result sort of thing actually. So, we will confine ourselves to something like this. And the results tells us something called proportional navigation guidance, which is there for a long time really. tells us that AM is nothing but NVM lambda dot actually. Okay. So, that means if I apply a lateral acceleration perpendicular to Vm something like this, where it is proportional to Vm as well as proportional to line of sight rate actually. That means this angle rate, the rate at which it changes, I will make it proportional to Vm and proportional to lambda dot as well. Then ultimately it leads to this kind of an expression where n is known as navigation constant actually. And traditionally it has been shown before that if n is equal to 3, then it has some sort of a optimal performance actually. That is what the major observations before in a classical sense by many researchers. Then it turns out that formally it can be shown that n equal to 3 is nothing but an optimal guidance actually. That is what the main motivation of this particular lecture. I am going to take you through this example and prove that n equal to 3 is nothing but a linear quadratic optimal initial guidance actually. Anyway, so this is the problem and we want to solve this problem without knowing this. We want to come up with some sort of a lateral acceleration trajectory, lateral acceleration history rather, which will lead to this collision actually. Then we will correlate this expression with that and so that this can be represented something like this actually. Anyways, the system dynamics that is accounted for is quite simple, it is very simple rather. It tells that there is a missile and there is a target here, the situation is slightly reversed. Okay. I have actually taken this example from Bryson and Hu book actually. So, that book uses some sort of a notation like this, so I thought I will just follow this way. Anyway, so missile is here, it moves with a velocity v, okay, and there is a target here. So, this is LOS actually, line of sight. Okay. What we are applying is a lateral acceleration perpendicular to v, which is direction A, okay, and this is the velocity vector capital V, and this is a this is the velocity vector along the line of acceleration basically. Okay, so and if you have this this one, okay, this is V and Tf minus T is something called T go. Okay. So, V into Tf minus T will take you there actually, assuming V is constant. Okay. So, the velocity, missile velocity is assumed to be constant. Okay. And also on the way we will assume that this angle, that sigma, what you see as line of sight angle sort of thing, that remains small actually. Okay. So, the whole idea here is to somehow close this yt has to be nullified, and if Tf computation is proper, that means this fellow is no other, I mean this missile, it cannot escape, it has to go to the target actually. At t equal to Tf, it is going there. The question is, by the time what this is called something called downrange actually, by the time the downrange becomes 0, your height should also become 0. Okay. Then the point lies on the target sort of thing. So, how do we do that? We will consider the system dynamics as something very simple. Second, I mean these two first order kinematic equations rather, V dot equal to A in this direction and y dot equal to v obviously. Okay. So, cost function what you are interested in is to minimize the yf as much as possible. So, this the penalty function outside the integral, and we are interested in some sort of a lateral acceleration minimization also, primarily because lateral acceleration leads to turning, and the moment something is moving and turning, the projection area to the fluid flow is larger and it essentially leads to something called induced drag actually. Induced drag is the primary factor for reducing the velocity and all that. We do not want to enter too much of lateral acceleration, so that we can preserve the velocity, that means we can preserve the energy actually. Essentially it leads to a high impact velocity as well as a larger range actually, things like that. Those are the benefits by having a minimum lateral acceleration. And an additional benefit is for a minimal if your lateral acceleration demand is minimum, then obviously through the autopilot loop and then the control loop and all, your fin deflections will also turn out to be minimum actually. And remember, fin deflections are typically bounded by certain values and all that actually, their rates and their values and all that. So, having lateral acceleration as minimum as possible helps us in several other things actually. Okay. So, we account for this this a square minimization on the way, but the primary motivation is to minimize yf actually. Okay, yf should be as close to 0 as possible actually. Just the reason why this cost function is selected. So, the problem is a this it is not a hard constraint problem, it is actually a soft constraint problem. Okay. And then this soft constraint problem tells us, okay, that y f has to be as close to 0 as possible at the end, while on the way lateral acceleration should be as close to 0 as possible actually. This optimal LQR formulation has this cost function as well as this system dynamic. Now, to proceed further, we first have to formulate exactly put it into the LQR framework, and for doing that we define a state vector, okay, v and y, that is the state vector, u, that is lateral acceleration which is nothing but a, that is our control vector or control scalar rather here. And once you define that, then you can represent the system dynamics as x dot equal to a x plus b u, where a and b turns out to be like that. Okay. And similarly, because there is nothing in the state side here, the q happens to be all zeros 0 0 0 0, whereas r happens to be 1 in this framework, and SF happens to be like this 0 0 0 c. Remember, the weighting is c times yf, and yf is the second component of the state vector. So, it turns out that c should not appear here, but should appear here rather, just because the definition of state vector is Vy and not Yv, okay, like that. And also this time to go definition is what I told, Tf minus T, that is the time to go definition actually. That means, how much time is left out for me from here to go and engage with the target actually. Okay. So, then following our results that we discussed a few slides earlier, we first go back to this augmented state transition matrix x dot and lambda dot, which is given something like that. Now, we have all these matrices, right, A we know, B we know, Q we know, R we know, SF we know. So, using all this augmented state matrix, I can write it something like this, okay. And then if I substitute all that, it turns out to be like that, and solution happens to be x of t lambda of t is nothing but phi of t t f into x t f and lambda t f actually. Okay. So, essentially remember, this is a linear time invariant system. So, phi of t t f is nothing but phi of t minus t f, that is the standard results in linear systems theory. Okay. You can do that as long as the system matrix is time invariant actually. Okay. So, what is the thing? We want to compute some sort of a, because the time invariant case, we can also compute this phi of t minus t f actually really. First we compute phi of t, and then we will substitute t wherever t appears as t minus t f actually. So, what is phi of t in this scenario? Nothing but e to the power a times t, that is the standard result. So, a already we know, this is the system matrix. So, what happens to be like e to the power a t is nothing but okay, let me okay. So, e to the power a t, okay, turns out to be like something like I plus a t plus a square t square by 2 factorial plus a q t q by 3 factorial, like that actually. So, we have to actually evaluate in this case we have a. So, everywhere it is a sort of thing. So, first we have to evaluate a, we already know matrix. So, a square is how much, okay, then a q is how much, like that actually you have to evaluate. At this point of time, I also like to tell that this is evaluation of e to the power a t using this polynomial expansion sort of thing, or infinite series expansion is not a very efficient way of doing things. There are other ways of evaluating e to the power a t as well, but we will follow one approach, okay, here to demonstrate the idea there. But somebody wants to follow some other approach, then it can also be done. For example, e to the power a t, there is another standard results that it is nothing but Laplace inverse of S I minus A inverse actually. Okay. So, those of you want to follow this way, okay, I welcome you to do that also. Resolve the problem taking that e to the power a t is nothing but Laplace inverse of S I minus A inverse. So, if it is A, it has to be A also basically. Okay. All right. Anyway, we will proceed with one approach. So, A we know, we will just evaluate A square, and A square happens to be something like this, which is actually good to see, because once you see all zeros here, including the diagonal elements, okay, one triangle is completely 0, then it is something called idempotent matrix. That means, you keep taking more and more powers, at some point of time some power will become 0, and hence all other powers there onwards will all become 0. That means, the series which is actually an infinite series truncates at some particular power. That means, the expression does not contain any approximation errors actually. So, this is the situation here. So, A being like this, A square turns out to be like that, and A cube turns out to be like this, and A fourth is all zeros. So, from there onwards A fifth, sixth, seventh, everything is 0, and hence we can write the polynomial e to the power A t up to third power only. So, this is I plus A t plus these terms and all that. Now, we know A square also, we know A q as well. So, we can put it all that, and it turns out to be something like this. Now, this is, remember, this is phi t. Now, what you are interested is phi of t t f, that means phi of t minus t f. So, wherever t appears, we substitute that as t minus t f sort of thing. So, this is what our state transition matrix in this particular situation actually. Okay. So, using this, okay, we don't want to keep on taking t minus t f carrying forward and all that, and it appears heavily in missile guidance literature also basically. So, we define that as something like t go, time to go, and this is by definition is nothing but t f minus t. So, wherever this t f minus t appears, it is actually t minus t f, but it is nothing but minus of t f minus t sort of thing. So, wherever that term appears, we substitute by t go actually. So, for example, this is nothing but minus t go, this is actually t go like that actually. Okay. So, we substitute this is t go minus t go like that, and get it something like this. Now, we have got this partition, that means, it started with a two dimensional state. So, this is a 4 dimensional matrix 4 by 4. So, we partition that and get this phi 1 1, phi 1 2, phi 2 1 and phi 2 2 actually. So, x of t can be written as like this. Okay. That means, this can be always written as something like, that is what we defined before, as something like state transition matrix for x. Now, we have phi 1 1 of t t f, t minus t f rather whatever, and phi 1 2 of t minus t t f as well actually. Okay. So, this is there available, that is available. SF we know, because SF turns out from the system formulation actually, the problem formulation. So, everything we know. So, we can evaluate this state transition matrix x of t t f actually. So, if you put it back, all the expressions that we know, it turns out to be something like this. Phi 1 1 is this expression, this part, okay, and then phi 1 2 is that part. Okay. You put it together, phi 1 1, phi 1 2, and SF is that part, okay, this part. So, put it together and then evaluate these expressions, it turns out to be something like this. And similarly, for lambda, the state transition matrix for lambda can also be evaluated through this expression, and phi 2 1 is available, nothing but all zeros, and phi 2 2 is also available. This is the matrix. So, we put it, and then SF turns out to be like this, and hence it is all like this. Okay. So, x of t t f is somewhere like this, and lambda of t t f turns out to be like this actually. And hence, lambda t, this is the expression that we we could notice that. So, lambda of t nothing but lambda of t t f into x of t t f inverse times x t, that is the standard results that we have. Now, we have lambda of t t f, which is nothing but this, and x of t t f is nothing but that. So, you can put it back, but remember there is an inverse operation still going on here. You have to take a symbolic inverse here to get the solution actually. Anyway, so this is what is lambda as a function of x, and hence finally, the control u is nothing but minus r inverse b transpose lambda, where r we know, okay, b we know, and lambda we computed just now actually. Okay. So, we substitute the expression for lambda, expression for r inverse b transpose taken together sort of thing turns out to be like, remember r is nothing but 1. So, r inverse is also 1 here, and b transpose is what you get here. Okay. So, this is what it is, and then we put lambda is nothing but that. So, we substitute it here and you simplify this 2 by 2 matrix inversion can be done symbolically rather easily. You have this 1 over determinant and then you can take adjoint adjoint elements, okay, very cofactors what I mean very easily by 1 over determinant. Then what will happen is this adjoint matrix turns out that this diagonal elements will extend the place and off diagonal element will change the sign actually. Okay, so, you can use all that, or you can go ahead and compute the inverse symbolically yourself, okay, starting from first principle and all that. Then it turns out that u of t, or what is a lateral acceleration, takes this form finally. That means, if I know v and y, I can write it this way, and also I need to know t go as well. Okay. So, finally, the solution of what we need to apply to get it there to capture the target happens to be this expression, and especially if c goes to infinity. Okay, that means, okay, what is the implication there when c goes to infinity? It all means that yf goes to 0 as a hard constraint actually. We are least bothered about minimizing the lateral acceleration on the way. Induced drag component is not our concern at all. In this situation, okay, you remember there is a 1 over c term here, that 1 over c will go to 0, and then you can further simplify the expressions. Your t go square will cancel some term and things like that way, and it will arrive at this expression actually. Okay. Now, just hold on for a second, just we will note it down for a second and then proceed further to different approach actually. Now, what happens here? Let us assume that sigma is tends to 0, sigma is small. So, I can write 10 sigma is nothing but sigma sort of thing. So, under assumption this is angle. So, remember this clockwise thing. So, we just put minus sigma sort of thing. So, 10 sigma, okay, or rather 10 of minus sigma, whatever we can call, is nothing but this angle also, same thing. Okay, this happens to be something like this by this basically. So, minus sigma is nothing but this divided by that is nothing but v into t minus tf minus t, and we assume v is constant. So, we can take it out and then this expression turns out to be like that. Now, what is sigma dot then? Okay, this is sigma which is with a negative sign and all that. Okay, so, now I can express sigma dot as well. So, minus 1 by v I will take it and then take the derivative of this, which happens to be this times the derivative of that y dot, okay, minus y, okay, times the derivative of this which is minus 1 actually. Okay. So, you substitute all that and then get it somewhere like this. Okay. So, what I notice here is like what we notice, if you just take v into sigma dot and multiply with 3, then it turns out to be this expression. V into sigma dot is that, and 3 times v into sigma dot is nothing but 3 times that. And what we obtained here is same thing basically. So, what it turns out that this expression what I have here and this entire expression I can substitute as 3 times v sigma dot. That is what I told you before, that n equal to 3 actually leads to an optimal guidance loss. Essentially, we started with this expression, right, this one. So, it happens to be n times v times lambda dot, or in this particular case sigma dot actually. Okay. And I told that n equal to 3 leads to some sort of optimal result, and that is what we just showed, that n equal to 3 is nothing but an optimal guidance actually. But remember, this P n guidance is an optimal guidance provided there are several conditions needs to be met, because in general P n guidance tells there is a navigation constant n. Okay. So, under the situation like this, that means we consider linear engagement dynamics, okay, and we also consider non-maneuvering or stationary target, that means a very slow moving target, that means the missile has velocity advantage, okay, and the LOS angle is not high. Okay. We assume that this expression, right, 10 sigma equal sigma sort of thing. So, LOS should not be high, LOS angle should not be high. Okay. Then induced drag minimization, that means through lateral acceleration, sometimes lateral acceleration is also called as latex, is a short form of lateral acceleration sort of thing. Okay. So, induced drag minimization, that means through lateral acceleration minimization, that issue is ignored. Okay. We are not bothered about that. Okay. And lastly, this n equal to 3 has to be used. Okay. Under those situations, P n guidance is nothing but an optimal guidance actually. Okay. So, this is just one way of deriving the P n guidance relationship through optimal control. Obviously, there are other ways approaches as well, and probably we will see one or two approaches as we go along that way actually. Okay, as we proceed further in this course, sometime down we will see how the other techniques can be brought in, and then we can get better and better results also basically. We do not have to really assume, let us say the target is non-maneuvering or stationary. We can actually assume the target can move, target can maneuver. Then what are the things that you can talk about? We will talk something called augmented PN and things like that. So, we will see some of those things as we go along through this course probably later. Now, in this particular class, as I told, we will also see some frequency domain interpretation, and then we will study this robustness margin sort of thing. Okay, robustness margin derivation I may not be able to do this class. We will just talk about the results that are available and why this LQR is popular is one of the reasons is also because of this issue. It gives some sort of a very good robustness margins actually. Anyway, so before going there, we will study this frequency domain interpretation first. So, let us start there. So, what happens? The optimal trajectory, that means the closed form trajectory happens to be something like this. Now, I assume that everybody knows what I am talking now, because x dot is Ax plus Bu, but u is nothing but minus R inverse B transpose B times x. So, I have substituted that, and then this is the gain matrix R inverse B transpose B. Okay. So, equivalently I can write A minus Bk times x actually. This is the closed loop system dynamics, and hence the optimal trajectory is dictated by this steady equation sort of thing. Assumptions on the way, A B is stabilizable and A and square root of q is observable. So, that is those are standard assumptions for LQR solutions and all. Now, here we define an open loop characteristic polynomial, okay, which is nothing but Si minus A determinant actually. This is a very standard linear systems concept. If I take Si minus A and evaluate the determinant, that will turn out to be a nth order polynomial in S basically. So, that we talk about as open loop characteristic polynomial. S is the Laplace variable actually. Now, what is a closed loop characteristic polynomial then? Okay. It turns out that that is what lambda C of S, what is defined that way, is Si minus A minus Bk. You see, this is your lambda open loop, delta open loop, delta of S, Si minus A, and the closed loop characteristic polynomial is delta C is actually, that is defined something like this, Si minus A minus Bk, because that happens to be the system matrix actually. So, open up the bracket, you can write it this way, Si minus A plus Bk sort of thing, and this same thing, okay, can be further manipulated and written something like this. Say I consider Si minus A now together sort of thing, and then Bk I will multiply Si minus A inverse into Si minus A, that is nothing but identity. So, Si minus A I will put it here one component, and Bk times identity is nothing but Si minus A inverse times Si minus A, this is algebra manipulation sort of thing. Once we do that, turns out that Si minus A that appears to the right hand side, because I can also assume an I here, identity here, and I take out that, and also we have the standard result, determinant of A B is nothing but determinant of A into determinant of B. So, using that result, I can take this one, this determinant is nothing but determinant of this one, the first one, into the determinant of that one. Okay. Now, what is determinant of Si minus A? There is nothing but open loop characteristic polynomial. So, I can write it this way. So, a closed loop characteristic polynomial is given as something some matrix, okay, times the open loop characteristic polynomial, and this particular matrix what you see here is something called return difference matrix. It is a very standard terminology sort of thing actually. And on the way people also use something called loop gain matrix and all that, that is defined as something like this actually, only that part with a negative sign. Okay, that is the loop gain matrix. If you put I plus and all that, that becomes return difference matrix sort of thing. Now, Kalman equation in frequency domain is what we are interested in. So, we will start Riccati equation. Start with the algebraic Riccati equation. So, we write it this way, okay, And then there is a further algebra manipulation here. Okay. To begin with, what we do is add and subtract this term S times P. P is nothing but the Riccati equation matrix. So, SP, okay, something like this, and minus SP. So, we are not whatever that, we are just adding and subtracting SP term actually. So, when you do that, okay, this happens to be P into Si minus A here, and Si minus A transpose into P from minus Si minus A transpose, we multiply by P, and then this K transpose R K is equal to Q actually. Okay, you can manipulate that also, because K is nothing but this R inverse B transpose P actually. So, if you notice that, then this entire thing R inverse B transpose P is nothing but K, and then you can multiply, I mean you can insert some terms and all that, you can write it this way actually. So, we keep it aside, and then we define something like a phi of S is nothing but Si minus A inverse, and with this definition phi of minus S is nothing but you just substitute minus S as S, wherever S exists you put minus S there, it turns out to be like this. So, phi of minus S transpose is nothing but that, but inverse and transpose can commute. So, we can put the transpose inside and take the inverse out, and then this transpose turns out to be nothing but A plus B transpose is nothing but A transpose plus B transpose. If you use that, Si is a symmetric matrix, so transpose does not matter. So, it is minus Si minus A transpose whole inverse actually. So, that is the observation what we have here. Why we need that? Because this already there is a term like this, okay. So, that somehow we want to kind of interpret it that way and then proceed further basically. So, now what we do is write this expression in terms of this phi S and phi of minus S, and then pre multiply by this one and post multiply by that one, both sides actually. Okay. So, if you carry out this longhand algebra, it turns out that this equation can be rewritten something like this something. Okay. Now, this K is defined as like that. So, R K, if I take multiply both sides, pre multiply both sides by R, turns out to be R K equal to V transpose P, and if I take transpose of both sides, then it happens to be K transpose times R, remember R is a symmetric matrix again, is equal to nothing but P transpose again, which is P is a symmetric matrix as well, times B. So, this is nothing but K transpose R is nothing but P times B. So, using all this and then adding R on both sides, whatever you have, you add R on both sides, it can be written something like that actually. Okay. So, this is I mean if you write it this way fine, or you can also write it this way, because phi of t, now you can substitute what is phi of S, phi of minus S and things like that. Then essentially this equation leads to same thing as that actually. Okay. Just by substituting the definition of phi of S and phi of minus actually. So, this particular equation that you see here is nothing but the same Riccati equation written in the frequency domain sort of thing. Okay. And this is not called a Riccati equation, but it is called something like Kalman equation. Okay. Because Kalman is the one who came up with this, looks like, and then this is the what is called as Kalman equation in frequency domain actually, for control design by the way. Okay. Kalman equations can be very famous for filter design as well actually, but this comes from this algebraic Riccati equation for control design. So, this is actually Kalman equation for control design. Now, the beauty is we can use this equation to come up with the gain matrix, or in a particular example problem, and we do not need any of those solution of the Riccati equation and things like that actually. Let us go through an example and make our ideas a little more clear. So, we take a double integrator problem, x1 dot is x2 and x2 dot is u sort of thing. That means, x1 double dot is nothing but u, that is kind of a double integrator problem. So, performance index, we take a standard LQR performance index, something like this. Okay. And this by the way, there may be there is a small mistake here, probably this is a half term there. Okay. All right. Now, this is the problem, there is a cost function and there is a system dynamic actually. So, we have to first identify various matrices. So, A happens to be like this, B happens to be 0 1, Q happens to be identity because both the terms are here, x1 square, x2 square, and r happens to be 1 because u square is available. So, all this a, b, q, r is available now. Now, what happens? Remember, we want to apply this term actually. So, you have b are now available, q available, r available, a available, like that actually. Okay. Now, the Kalman equation is nothing but that. Okay. Whatever you see here, it can be written as something like this. Okay. Where Si minus A inverse, okay, happens to be like this. Yeah. Okay, because Si minus S A is available, A matrix is available. So, you calculate Si minus A symbolically and then take Si minus A inverse symbolically also basically. It will turn out to be like this. Now, we define gain as K1 1 K1 2. Remember, gain has to be a row matrix in this particular case, a single input system anyway. So, gain has to be K1 1 K1 2. We do not know the values of K1 1 K1 2 yet. We want to compute it using Kalman equation actually. Yeah. So, what we do? We substitute that, okay, in this equation especially directly, and we can now retain whatever K1 1 K1 2 symbolically, okay, and this ultimately after simplification of this matrix multiplication and things like that will lead us to this kind of an expression actually. Okay. And here we can actually equate the coefficients of various powers of this 1 by s square, 1 by s cube, s fourth like that. Okay. And ultimately we will see that okay, 1 is equal to 1 anyway. This is otherwise it is 2 k1 1 minus k1 2 square is nothing but minus 1 here, and then k1 1 square is nothing but 1. So, if k1 1 if k1 2 if k1 1 square equal to 1, then k1 1 is 1. Equating this to that, there is a coefficient 1 here, that means k1 1 square is nothing but 1. So, k1 1 is 1, and k1 2, if 1 2 once you have this k1 1 1, and this expression happens to be minus 1 basically. So, this is minus 2 and then it is minus 1, and then you take it to the other side, it becomes 3, but that is k1 1 2 k1 2 square equal to 3. So, k1 2 happens to be square root of 3. And obviously, you can always argue what happens to these plus or minus things and all that actually, but then turns out that if you select k1 1 1 and k1 2 as square root of 3, then it leads to a stabilizing controller actually. Okay. All other things will not lead to stabilizing controller, and which happens in the Riccati equation solution directly also. Like you will have a multiple solutions for Riccati equation, and you select the one which is positive definite solution actually, and then only it will lead to stabilizing controller. So, similar ideas exist here, and out of we eliminate these minus roots and we take the positive roots and come up with the gain matrix. And this gain matrix 1 square root of 3, that matrix can be also derived by solving this algebraic Riccati equation formulation, and I encourage all of you to do that using your pen and paper Longhand algebra actually. Don't really have to go through this MATLAB formulation and all that. But quickly you can also, those of you do not have time or want to have quick answer and things like that, you can also use this LQR function of MATLAB and just type in these values a, b, q, r, and immediately the gain matrix will pop up, and that will be nothing but 1 and square root of 3 basically. So, this is about this how do we use this Kalman filter, and how do you do this how do you make use of this Kalman equation rather for control design for problems actually. But this is not the main motivation for having the Kalman equation actually. People come up with this, and then the further analysis tells us that what is the frequency response actually. That means what we know is some sort of an Nyquist diagram, Bode diagram and things like that. Can't we really do that actually? And answer turns out to be yes. Then what happens is like what we do in linear system dynamic analysis, we substitute S equal to j omega, okay, and then using that analysis we will proceed further and then derive this root locus diagram, Bode plot, Nyquist plot, all sort of things actually. So, that analysis I will not cover here, but those of you are interested, actually this part of the thing I have taken it from D.S. Naidu book, and those of you are interested, you can see the book for further analysis actually. But the interesting result turns out to be something very good, and it turns out that this entire result LQR formulation has a very good robustness property, and the gain margin happens to be minimum half and maximum there is no bound actually, it can be infinity also. Okay. And phase margin can be at least 60 degree, it can be more than that, but at least 60 degrees is guaranteed actually. All that of course happens with exact state feedback. Okay. If the exact state feedback is not there, that means you use some sort of a estimated state and things like that, then these margins are concerned, it does not satisfy these margins. Then there are concepts of LQG, LTR and things like that, we will probably see it down the line actually. But assume that exact state feedbacks are available, and many times it does available by the way, as long as you talk about controlling your own system dynamics, okay, without the need for an exogenous input for controlling. In other words, unless if you talk about a missile guidance problem, we need to know where the missile is, what angle it is going, whether it is stationary or moving away and things like that. Those information cannot be declared by the good sensors in the target actually. Target uses its sensors to do its own job, but it cannot reveal its own strategy and things like that. For that we have some sort of a seeker or radar measurement and things like that. There it is a need for some sort of estimation in the loop actually. Otherwise, now for many costly systems, that means many good systems. So, we have good sensor equipments and all available. So, if the system is heavily equipped with good quality sensors, then you can actually get all the state feedback without a estimation in the loop sort of thing actually. So, then you can actually implement it and you can show that gain margin is minimum half or maximum infinity and phase margin is at least 60 degree. By the way, there is a little bit interesting discussion here that earlier days these control gains and all were actually synthesized using analog devices. So, there was some chance of having this gains, what you intend to do, intend to give it to the system, the actual gain would have been something different actually. Okay. And that is no more a concern, because it is nowadays it is all digital control actually. So, we actually compute it in a computer and then hence feed it back to the system. That means there is there is no relevance of gain being inaccurate and things like that. But still gain margin is a very important concept, primarily because any amount of system parameter inaccuracy will ultimately reflect in some sort of an equivalent gain perturbation in the closed loop system. If you have system parameters which is not what you assumed in the control design, something else, then it can be equivalently described as some sort of a perturbation in the gain value actually. So, that is how it is still important, even though we have digital computers actually. And similarly, phase margin has a time domain interpretation of what is called as delay margin nowadays. And delay margin is if you remember, this phase margin essentially comes with this time delay input of the signal actually. So, then delay is an inherent phenomenon. You can have sensor input, sensor output delays, you can have transport delays, you can have computation delays and things like that. And with the advancement of all these technologies and computers, the gain margin, the phase margin or the time delay margin is a high time delay margin is probably not required, because things can be done in a very efficient way. That means the good margin requirement from phase point of view may not be very stringent nowadays, but we certainly need something, okay, some gain margin, some phase margin as well, because no matter how fast is the computer, no matter how far, whatever it is, there will be some amount of transportation delay, some amount of computational delay and things like that. So, the system must have some sort of a positive phase margin, okay, for successful operation actually. There is another, there are many concepts, ideas like that. For example, this gain margin and phase margin, they have to be positive for a stable system, and they happen to be both 0 at the same time. It cannot have like 1 0 1 non 0 and then the other one becomes 0 later and all that. They can start with something, and but then when they happen to be 0, they happen to be 0 at the same time actually, after which the system goes unstable actually that way. So, anyway, but those concepts of gain and phase margin are classical control concept. Interested students can find many typical books around that to have lot more ideas there. The whole point here is, if you have LQR design, it is optimal control design, and essentially it not only does a lot of jobs compared to, let us say, a typical PID controller or pole placement design, because remember, pole placement design is okay provided you have single input. If you have multiple input, then there are not so easy things to do or not so good things to do actually. Then we can talk about control scheduling, things like that, but then it is not very scientifically done. The one way of control scheduling is through LQR control actually. So, LQR has a lot of other things, a lot of good properties associated with that, and hence it has been heavily used as well actually. So, with that I think I will stop this lecture and we will see the further things in the next lecture. Thank you.